In this video, we'll take a look at more properties of polymers and some key attributes of them before we get into some examples. So one thing that is very common with polymers and polymerization, especially with thermosetting plastics, is the idea of cross-linking. Cross-linking polymers is it's a simple kind of concept. And where it comes from is, especially with thermosetting plastics, a lot of them lack strength in their chain forms. So imagine, if you will, that a polymer exists and it's just a series of long chain molecules. Well, on their own, these chains will just slide over top of each other and not have a whole lot of tensile strength. What cross-linking does is it starts to introduce chains, links, kind of like rungs on a ladder, that are going to restrict the movement of those chains across each other. And so instead of sliding over each other and having a very elastic, kind of um, tendency, well, not even elastic, just a soft kind of tendency, those cross links make it so that it's very difficult for those chains to move. And so they just kind of stop sliding over each other. They become more fixed in place, more rigid, and that leads to greater strength overall in terms of their physical properties. Now, these chains that are made, these linkages, are chemical linkages. That is, we're getting chemical bonds forming in between these strands that are causing these increases in strength. And the more of these chemical bonds we can introduce, the higher the strength will ultimately be. And so here are a couple of common examples. In this first example on the left, this is the process that is known collectively as vulcanization. Vulcanization is the introduction of sulfur linkages between these strands of polymeric rubber. And so vulcanization is the process by which a tree sap rubber can be strengthened to the point where we can get something hard and rigid like a tire. Here's another common property, another common example of a reaction. This is, we can either call it silly putty or slime. And what we have here is we've got a polyvinyl alcohol polymer that we have introduced a borate ion into, and the borate ion attaches through these double cross linkages, and we get polyvinyl alcohol starts off as kind of like a really thin glue viscosity and consistency to a slime that, depending upon the number of cross linkages, we can actually get into more of a semi-solid state that has capability of bouncing and other things. So that's cross-linking. Another common phenomenon in polymers is something called autopolymerization. In autopolymerization, what we have is there's a tendency for some monomers to be able to form their own polymers without really any kind of outside influence. So if you remember from the previous video, we talked about there were three stages of polymerization. There is the initiation stage, the propagation stage, and then the conclusion stage. Well, autopolymerization occurs basically without the initiation stage. You don't need to add another chemical. What you end up doing is, it forms it on its own, gets hit by light, or just naturally decomposes on its own. And the way that you combat this is through the use of inhibitors. Now, one common place where we see autopolymerization to a degree is in high carbon diesel fuels. If you've ever heard of the phenomenon of a diesel engine gumming up, um, polymerization has a lot to do with that. And the way that you fight that is you either change out your fuel frequently, or if you know you're going into long-term storage and you don't want to drain the fuel tank, you add inhibitors. And the inhibitors work by pretty much slowing down the reaction of polymerization and preventing those clumps of polymer from forming in the first place. Now, what happens when polymers decompose? Well, we know that polymers, because they are so prevalent, and because the reactions that they make when they decompose usually produce flammable gases, we have to be really careful about their decomposition and then ultimately their combustion. And so we know that most natural synthetic and synthetic polymers are combustible. We expose them to a flame, they're likely to ignite. Some will melt, and some will kind of decompose and gasify into either the substance that they were made from, the monomer itself, or even simpler substances still. We also can see that in some cases, the surfaces of the polymers will char. They'll actually take on a black carbon residue. But because of their high carbon content, when these things burn, they burn with a considerable amount of heat. And because of their high carbon content, they usually do not burn completely. We usually have a series of byproducts that come off of them as well. And because of that, we tend to see, as a matter of principle here, smoke, carbon monoxide, other hazardous gases, and vapors and fumes. So, not surprisingly, when we have something that is dangerous and produces dangerous byproducts, there's a lot to be said about watching out for them. One of the side effects of this phenomenon of the vaporization is something called flashover. Now, flashover is an interesting phenomenon that occurs where a fire could be on one side of the room and it hasn't spread to the other side of the room yet. But the heat generated from that fire is so significant that it just keeps generating more and more heat, and it causes the polymers on the other side of the room to start to decompose. As they decompose, they're creating more flammable vapors, and eventually the fire spreads rapidly, bang, from one side of the room to the other without going across the floor, without going across, it goes just straight over from the air, and now you have fire on both sides of the room. Now, for a demonstration of this phenomenon, I'm actually going to kick it over to another YouTube site here. So, watch this video. I'm linking to it on with a little card here. I'm also going to put it in the description. It's about 5 minutes long. Actually, only takes about 3.5 minutes to get to the flashover, but it's a really cool demonstration of just how quickly this kind of thing happens and how it happens. You can actually see in the video how the chair, how the couch, how different parts of the room start to vaporize under the stress of the heat, and how all of that just impacts and ignites all in one quick moment and sets the whole room on fire. So give it a watch. It's gonna be it'll be worth your time. Now, as I said before, the heat of those fires is substantial. One of the reasons why is the carbon content of the fuel itself, of the polymers. And so we can estimate that most common polymers will actually evolve about twice as much heat as when compared to an equivalent mass of wood. Now, among the dangers of polymers when they burn, obviously carbon monoxide. Carbon monoxide is the most prevalent gas because you've got all of that carbon burning, you're eventually going to run out of oxygen, and it's going to start taking shortcuts, and we're going to get all that soot and that carbon monoxide. Now, depending upon what the other polymer components are, you could find yourself inhaling hydrogen chloride, which when it mixes with your the water vapor in your body becomes hydrochloric acid, ammonia, cyanide gas, sulfur dioxide, nitrogen dioxide. And obviously you're getting a lot of smoke and a lot of soot here as well, because for the same exact reasons, all that incomplete combustion. And so we'll end this video by looking at just a couple of examples of this kind of fire taking place. And so this is an example of a common mattress fire. Now, it's hard to see here, but there are actually two mattresses in the photograph. There is one here, and then there's the second one that you can see here with all the springs exposed. The difference between the two is that the top one was treated with a flame retardant of some sort. And you will notice that it's going to burn a lot more slowly than this one underneath, which was burning so quickly that you can actually see the structure of the springs in the mattress as it is burning. And then this photo shows those same two mattresses after the fact. And you can see that the bottom mattress, which was burning considerably, has significantly more smoke, has significantly more charring than the top mattress does. And so that's one of the rules where a flame retardant can actually help by slowing down that reaction, slowing down that combustion, slowing down the ability of that polymer material to actually burn and to actually vaporize. So that's all for this video. In our next video, we're going to start looking at some different types of polymers and some of the properties and reactions that they undergo. Until then, have a good day.